often you may be called upon to solve a problem for which there's no immediate solution. If you're asked to sort a collection of values, that's easy to do. It's an easy decision to determine if a value is smaller than or greater than, and you apply that enough times, you get a sorted answer. Mathematical algorithms also, there's a definite answer you're trying to reach. But sometimes there are problems where you can't know the best way to solve it. However, once you've solved it, you can recognize that you have a solution. And if we put this all together, we're now setting the stage for what's called a brute force approach to solving a problem. I will still call this an algorithm because it is a complete step-by-step solution that explains how to solve a problem on a deterministic sequential computer. It's just that there's very little intelligence involved. It only works because computers are so fast that they can solve problems that would be otherwise tedious for a human to solve. And that is the nature of this module. How do you take something that is otherwise not worth my time as a human to solve, and I just write a small program to let it work overnight, maybe for a couple of days, and come back with an answer? And that's where we're going to start. If you've ever driven down Route 95 from Boston to Florida, no doubt you've seen the Cracker Barrel restaurants. And they're great stops, not just for the food, but every table has a solitaire game based on a pegboard, where you have a collection of golf tees in this case, which are the pegs, and they're structured in a triangular arrangement, 15, with one missing. And the goal is to try to jump one of the pegs over another peg to remove that peg from the board, and then eventually be left with just a single peg standing in the solitaire board. This is the common solitaire game that's been invented through the centuries. Very simple rules, but no simple solution. In fact, if you try it enough times, you might find yourself pulling your hair out because it seems so obvious that you should be able to do it, but at all attempts, you end up with 2 or 3 left, and you never get that elusive 1. Well, instead of trying to find an intelligent solution to come up with the proper sequence of moves, I would rather just say, let me find a brute force solution that will work in all cases. Let me explain. Here's my peg jumping game. There are 14 pegs and 1 empty hole. Now, to remove a peg, you've got to find one peg that you want to remove. That's the one I've identified with the X. And to remove that, you've got to jump over it from an existing peg to the empty hole on the other side. Each of the moves that you see in this particular triangular pegboard are either northeast, as this one is. To go from the red peg, you lift it up, you jump over the one you want to remove, and you end up in that empty hole. And in doing so, you've turned a board which had 1 empty hole into a board that has 2 empty holes. And then you repeat, maybe finding another peg to jump, to remove another peg until you have 3 empty holes, and so on. And that particular strategy, as you see here, can be applied repeatedly until you get down to what is hoped, a single peg remaining. I don't know where that single peg will be left standing. I don't even know if it's possible for that to be done. But I know I can write a program to carry out a sequence of steps to methodically try every possible sequence of moves. And at the end of it, it will tell me whether it has a solution or not. This particular approach that I'm going to describe, I've used for the past 20, 30 years. Whenever I'm stuck with a game or a puzzle that I'm frustrated at, or I just want to find a solution for, if the problem can be represented in a very small way, I can write a brute force approach that would just crunch through the numbers and produce my answers. And so what does a brute force algorithm look like? It takes a decision that says it's not going to try anything intelligent. Instead, it would just blindly try all possible move sequences from that starting point to try to get to a solution, whatever it is, in which a single peg remains. There are certain observations that you can make that make this particular game tractable. Specifically, with every move, the total number of pegs on the board is reduced. This one little observation gives you the hope that you will eventually come to a solution. If I have 14 pegs and I want 1 peg left standing, well, all I need to do is make 13 moves. So I know how many moves I need to do. The trick is finding out which ones those are and the order in which I make them. Another observation is that I can approach this problem the way that I would trying to solve a simple rectangular maze that you might have done as a child. You don't know where to go, so you just blindly go off in one direction. And if you get to the solution, great, you're done. If you don't, well, you've got to backtrack and work your way back to an earlier branch and try to go someplace else. That fundamental ability called backtracking or undo is what we need to do to make a brute force algorithm work. So I need to be able to not just make a move, but also undo a move. And the final point, it seems an afterthought, but it's worth reminding ourselves. This will only work if I can actually recognize a solution when I see it. And so I don't care where that peg will be remaining. I just want to have a peg remaining in some hole, and when I do that, I will call it success. So here's a quick way of speccing out the algorithm. I'm not going to use the standard spec sheet because, after all, for this particular problem, I'm not concerned with the time complexity of this. I want to work on small problems only. When you see, even for the small problems, how the time complexity is incredibly large, you quickly realize you can't use this for large problems. That said, there are a lot of these solitaire versions of games that are human scale, like tic-tac-toe, even chess, or Go, which is an incredibly complicated game and is still one that defies proper computers to implement. Chess has been solved, as you know, by the Deep Blue and other computer algorithms that will match up best against human players. And soon, I'm sure Go will be the next one, the next milestone that algorithms will achieve. But let's get back to our solitaire game. If I want to solve this, I want to think recursively, the way we're trained when we do algorithms. I want to break my problem up into a subproblem which is smaller than the original problem. Well, that's easy to do. To solve a board, all I have to do is make a move, any move. And once I've done that, I now have a problem size that's one smaller than the original one. And then I recursively continue. So that idea of updating the board state is fundamental to the way that this program works. And so my pseudocode here that's identified in the rectangle shows, to solve a board, I not only want to solve it, at the end of it I want to have a path, which is some sequence of moves that I've kept track of that remembers the exact arrangement of moves that I did to get to the final solution. When you do a rectangular maze, the path is structurally part of it. You have your pencil or your pen mark all the way back to the beginning, leading your way to the end. I need something similar here for a brute force approach. And so I will build up a path, which is a sequence of moves. And the way that I solve the problem is with hardly any intelligence at all. When faced with the challenge of solving a board, I say the following. Is the board solved? Return true. You can imagine this if I give you a board which is 15 pegs, 14 holes, and there's one peg left standing, you're solved. You know you're done. So that's the base case of the recursion. The more complicated case, which says how do I divide the problem up into a smaller problem, goes as follows. Given a board, I have to be able to enumerate all the possible moves that are available. And in the game of peg solitaire, I need to find the empty holes, and then I need to find a peg next to the empty hole, and then another one on the other side that I can jump over. This is not an infinite number. There's usually a very small number of moves available at any one time. Much like in a rectangular maze, when faced with a branch, you can usually go one or two different directions, but otherwise it's very manageable. So I need to compute all the possible moves for a given board state. That's another assumption that I have. But once I've done that, I use the following approach, and I do it methodically, and I don't leave anything out. I have a path that I'm building up. Those are my breadcrumbs that I'm keeping track of, my sequence of moves. I try a new move. I add it to my path, and then I actually execute the move on the board state to remove the peg. Then I recursively call solve with that new board state and say, well, can you solve that one? If that recursive call ever comes back as true, then I know that I'm done and I return true. So this is the kind of recursion which is doing a very large space exploration. But once it finds a solution, it stops immediately. It's a very powerful approach when you don't have any intelligence about how to choose your moves or which way to go next. However, if it turns out that the board that you did the move on, if you couldn't actually solve it recursively, then you say to yourself, well, looks like that move was a dead end. So I undo the move, what it did on the board, I undo. And I go on to the next move and say, well, let me try something else. If I ever exhaust all the possible moves that are available at a particular board state, then I know that this is not a solvable game, and I just return false. So the code is deceptively simple. Maybe 8 lines, as you see there, that's pseudocode. But it encompasses a very deep understanding of recursion, which is fundamental toward this algorithm, as it is with many algorithms in computer science. To solve a problem, you have to break it up into smaller problems. In this case, the smaller problem is just one size smaller. But I try each one of those in turn, and if any one of them ever returns true, I know I'm done. And if none of them return true, I know that I'm a dead end, and I hope that someone else will backtrack, undo another move earlier in the path, and start again. So this will try every possible attempt. Taking this and applying it to a particular problem requires you to face some specific issues. And what they come down to is a representational problem. The algorithm itself is very simple, but can we represent the board state in an efficient and compact way? Because I may have hundreds of thousands of board states to investigate. Is it possible to even describe all the moves that are available? And once I've done that, can I make it easy to execute a move on a board and then undo that move later if it turns out that I don't want that move? All of this together leads to what in computer science is known as a state explosion. If you try to solve a brute force algorithm on a problem that's too big, you might run out of memory. You might run out of stack space, which means your recursion never terminates. All these things are likely to happen, but if you try it on a small enough problem, you'd be surprised at the things that you can actually do and achieve. So before we go into the code, I do want to talk about the board state representation and the moves, because that is the fundamental challenge to implementing a brute force approach. The code stays the same. The only thing that changes is the way you represent the board and the way you represent your moves. It doesn't matter what the representation is. I'm just going to provide one here. You can apply the same thing for any game you might imagine. Tic-tac-toe, or even chess if you wanted to, although chess is too big to search in a brute force approach. Connect 4 is a little bit better. So let's talk about state representation. In the pegboard, there are 15 holes set up in this arrangement. I have to be able to find some way to record which holes contain pegs and which ones don't. So I'm going to use a Python dictionary for this purpose. And as you may know, a dictionary in Python is an associative lookup table that lets you associate a value with a particular key. In this case, I need to have some way of uniquely identifying each of those 15 holes. I could have used a number like 1 to 15. That would have worked. But then it would have been harder, I believe, to figure out what moves are valid. So instead, I've chosen to use a two-dimensional way of representing each hole. I'm going to assign 2 numbers, which I'm going to call the column and the row, with each of those holes. I'm going to arbitrarily call the lower left-hand corner one, marked in purple, 0, 0. It's not necessarily the origin like you would find in Cartesian coordinates, but I have to start somewhere. I'm going to call that one 0, 0. And if I look at the board from left to right, I can see columns that are moving, increasing size from left to right. I can also see rows that are increasing from the bottom to the top. So that lower hole marked 0, 0 has 2 neighbors. It has a hole marked 1, 1, which is directly northeast of it, and it has a hole 2, 0, which is directly east of it. And if you apply that basic logic, to go up means to increase your row by 1. To go to the right means increase your column by 1. So following this logic, the lower left-hand corner is 0, 0. The topmost peg at the top of the board is 4, 4. And then the rightmost corner peg in the far right-hand side of the slide, that's going to be 8, 0. Because if you look at the columns, there are gaps in the columns when I'm going from left to right. There's a space from 0, 0 in the lower left-hand corner to 2, 0, that's its neighbor. And then the middle one in the bottom row is 4, 0, and so on all the way up until you get 8, 0. When you go diagonally, you get to change one of your positions by 1. For example, from 0, 0 to 1, 1, I'm going northeast, so each one increments the row and the column. If I'm going southeast from 1, 1 to its neighbor below it to the right, 2, 0, I'm going to change, my column is increasing because I'm going east, but because I'm going south, my row is decreasing from 1 to 0. Having that representation fixed in your mind is essential to understanding the structure of the board and the type of moves that are available. Once I have that position in mind, I can represent a board, any board state, by a dictionary, which has a key, which is a tuple of a column and a row, and the value is true or false. There are 6 moves that you would see. I can move east to west. I can move southwest or northeast. I can move southeast or northwest. Each one of those has a very specific arrangement of the holes. For example, if I wanted to jump from the 0, 0 hole over a peg that was in 2, 0, ultimately landing in the hole 4, 0, that's a particular move which you can designate simply as the delta on the C column is +4, and the delta on the row R is 0. Similarly, if I wanted to jump west, my row delta would still be 0, but my column delta in this case would be -4. Through these very simple mathematical observations, I can clarify the full board state, I can identify all the possible moves, and with this in mind, we're now ready to carry out the Python implementation of the peg solitaire game. Let's show a full implementation in Python of a brute force algorithm for solving the peg solitaire game. After accomplishing this, you'll actually have the framework for solving any number of like-minded games. As long as you can represent the board state in some way and represent the valid moves, the core algorithm will remain the same. So let's get started. First, I want to say that this code that I'm about to write is a result of working on the problem for several hours. So you will not always get the best representation, always, the very first time. It may take some trial and error, as it did here, but I'm not going to show you all of my intermediate steps. I'm just going to show you the code that would be an ideal implementation of the pegboard problem. Let's first start with this idea that says I want to have the ability to start with an initial board. And when you think about an initial board state, it's going to have n holes. Construct a triangle solitaire game. And I start from the beginning by saying there's no need to restrict this to a 15 peg. It could just well work on a 21 peg or 28 peg, any kind of triangular board. So I'm going to try to build in some flexibility even at the very beginning. I'm going to construct a triangle game with n times n plus 1 over 2 holes, each filled with a peg, except for a specific omitted value, which I will call skip. So when you start the solitaire game, you put all the pegs in place, but there's always one hole that's empty. So I'll leave it at that. To do this, I need to represent the board somehow. I've already mentioned that I'm going to use the dictionary for this purpose. And so when I'm done, I will return in the board. However, I need to populate it with entries. And we know that I want to represent each hole by a column and a row designate. And it takes a little bit of time to figure out the exact strategy to use by identifying these points. Here, if you recall, I want my columns in the lower left-hand corner to be 0, 0. And then I want the row, the lowest pegs on the row would be 0, 0, 2, 0, 4, 0, 6, 0, 8, 0. So if I put all that together, I want to go from 0 up to 8 steps of 2. So that's how my columns are going to look. Next trick is going to be my rows. And for my rows, I'll have to do a little bit of work. And after you ponder this for some time, which again, I'm not going to do here, you realize that you want to do a different number of values for every row. The bottommost row has 5, then has 4, then 3, then 2, then 1. But if you consider the columns, if you start with the columns, however, the 0th column, the lowest on the left, has just one peg. And then the first column also just has one peg. It's in the middle of a diagonal. So we have to do a little bit of work here. And I'll just put this together, and then we'll look at the result. And when we're done, we'll see whether we actually have a board. This will create, for every column and row that I need in my triangular array, a true-false potential. In this case, they're all true. I start by assuming every hole has a peg. And then don't forget that I want to skip one, and so he's the one that I empty, and then I'm done. How do I know that I've made any progress? In this particular exercise, we're going to do a lot of going back and forth, writing some code, testing it out. It's really the only way you can get the representation and the moves just right the way you want. I'm going to create an initial board, which I'll call board initial 5, and right now I don't want to skip anything. Well, what have I created? It looks like it's a dictionary. It has a bunch of spots that presumably are the holes in the board. 0, 0, that's the lower left-hand corner. 4, 4, that's the topmost peg. 8, 0, that's the lower right-hand corner one. So it looks like I've got everything right. Let's just go through the board and make sure that all the values are actually properly entered in there. And it looks like I've got a mistake, and this is actually a simple error we can fix. The space on the board are properly marked, all of them except for this one here called none. And well, I didn't really have the right contribution here, right? I wanted to create an initial board where every square, every hole possible was filled with a peg, except for one that I designated as skip. Well, I didn't bother to actually make sure that I passed in a valid answer. So I just make a small little change over here, which is simple enough to say, if skip is in the board, then I make sure that that's the one that I leave out. Tiny little change just to make the code a little bit more robust. So now here, I have my initial board. There's my board. It has 15 holes. As it stands, this board is actually not interesting because there are no holes, so there are no moves that I can do. So I really want to remind myself that when I'm creating a board, I know in advance which particular hole I want to omit the peg from. Currently, as you can see in here, all the values are true. Every hole has a peg. And the one that I want to omit is the one that's at the center, just below the topmost peg. Well, the topmost peg is 4, 4, and the one below it, which is going to be the place I want the hole to be, is going to be 4, 2. I know that because it's actually 2 rows below the topmost one. So that means the coordinates are representing 4, 4 for the top one. This one would be 4, 2. So if I want to represent my board as the initial setup, where I skip the coordinate 4, 2, now I've got something. You'll note here briefly that my board still has 15 holes in it. All of them are filled with a peg except for one that's false, as you see here. And the one that's false has the key 4, 2. So now I've completed my setup for the board. Invariably, this is normally what you need to do to start with. And so now I'm ready to proceed to the next task, which is, how do I know if a board is done? Well, I know a board is done when it actually has only one peg remaining in it. Okay. How am I going to work on that? Well, we can start with this idea that says, if I'm going to identify which hole has the remaining peg, I have to find some way of clarifying that it's empty in all the other ones. This looks like it's going to be a lot of work. And we talked about this earlier. I need to be able to determine in advance an efficient operation for knowing whether the board has been completed or not. So what I'm going to do right now is choose a different approach. I know something about the pegboard game. I know that if there are 3 pegs, you have 2 moves to make before you have 1 left. So I'm going to claim I don't need a special function to evaluate the board state and determine if I'm done. If I ever make n minus 1 moves, and I know that I started with n being the total number of pegs, then I know there's 1 left standing, so I know that I must have a solution. So I'm going to leave it at that. I now have a board. I have the ability to determine when I'm done. Now all that's left to do is to put that code into practice, which I'll do now. And if you recall, I need to have a solve method that starts with this idea that there's a current path that I'm building up. This solves the board and updates path to reflect the sequence of moves. If it ever turns out that the total number of moves tells me how many pegs are left, then I know that I'm done. So let's look at it this way. Here's my board. It has 15 holes. There are currently 14 pegs there. So I need 13 moves. And then after those 13 moves, I know I have a solution. So I'm going to make a very simple observation here. If it ever turns out that the length of the path is equal to the length of the board minus 2, I know I'm done. I say minus 2 because I start with 15 holes. I take away 1 because that's the empty one, and the other 14 have pegs. So if I have 13 moves, which was the length of the board being 15 minus 2, if I have 13 moves, I know I'm done. So you have to be able to have that very rapid check to test if you've got a solution or not, and I have that in place. Now comes the actual algorithm itself. And the way that it was phrased was by saying, I need to check every move that's available. So I got to come up with a function to do this for me. For every move that's available, I want to make that move on the board state. That'll make the move with whatever move is. I'm going to write these functions shortly. And before I do that, however, I want to make sure that I add this to my path, appending it at the end, because after all, my path is a sequence of moves that I'm keeping track as I solve the problem. Every time I'm about to make a move, I push it onto my move sequence. And then as you see in a moment, when it comes time to undo a move, I will pop it off because I know that it led to a dead end. So as I try every possible move that's available, I update my path, I make the move. And then I recursively say, have I solved that subproblem? And if you ever find that you've solved the smaller subproblem, then you know that I'm done. So I actually have everything set up for the termination case. No matter what initial board I start with, I will try every possible move. And if I ever get to this point here where the length of path tells me that I've made 13 moves, I'm done, and then the whole thing will quit. But it may be the case that it didn't actually work, that I might not have been able to solve that particular subproblem, in which case I have to undo the move from the board. And then I have to remove that particular move sequence from my path. And in Python, there's a very quick way to remove the last element. You just say delete or del path -1. That'll remove the last entry from a collection. And if it ever turns out that I'm unable to find a way through from any possible move, then I return false and I say, I guess I can't solve the board from this particular situation. Everything is now in place. I still have to write some functions, but I've been able to translate the code from that pseudocode into an appropriate Python representation. Now what's really interesting is that particular code you see here. I can't tell you how many times I've written that, hundreds of times in the past 20, 30 years. It's the same every time. The only thing that changes is what's the representation of a board and what are the allowed moves and how do you represent them. So we've already discussed the representation of the board. It's now time to talk about moves. Let's write the moves function that returns the actual moves that are able to be made at any point in time given the board. As you know, there are 6 possible move types. I could be moving west or east in the pegboard. I could go northeast or southwest, or correspondingly, I could jump northwest, southeast. To capture all of that, let me write a function that returns the moves given a particular board state. I need to naturally find a way to represent my move. Well, the good news is that a move can be captured simply by the following. If you know a particular column and row, then the move is going to be a delta reflective of that point. So the lower left-hand corner peg is 0, 0. If I want to jump east, I'm jumping over the square, the hole 2, 0, and landing in the hole 4, 0. That kind of move is represented as a change in the columns of +4, but the row hasn't changed. So if I keep track of all my directions, that first move, which is an eastward jump, would be nothing more than +4 and 0. If instead I was jumping to the west, which means I'm jumping from the right to the left, then my column would be being reduced by 4, from 8, 0, which is the lower right-hand corner peg, to 4, 0, which is the middle peg in the bottommost row. That captures 2 of the moves. I've got 4 more to go. And for each one of these, I need to clarify what the delta is on the columns and the delta is on the rows. Let's tackle this one. If I'm jumping east and then north, so east first says I'm going to move 2 columns to the east, and north says you're going to go up 2 columns to the north. This is the jump which would go from 0, 0 all the way up to 2, 2, which is halfway up the left-hand side of the triangle on the outer edge. Similarly, if I said, let me go east, because I'm moving my column by 2, what if I was going south? So I'm going down the pegboard. This would be like, for example, starting at the highest most point, which is 4, 4, and ending up at 6, 2, which is on the rightmost edge, in the middle side of the rightmost edge of the triangle. And for completion, I now have the last ones, which is if I'm going to the west, I might be going to the west, and I might be going north. This is northwest. Or I might be going west, and to the south, that's southwest. Those are my 4 directions. Each is a delta, first column, and then a row. The reason why this works is because the representation of the board makes it possible to work. It has to be the case that you can quickly and efficiently determine all possible moves just by knowing a particular representation of the board. If this was a torturous problem, then the whole performance would suffer. So I have to make it as simple as possible for me to do the execution. So let's fill out now what the moves does. It's a very sort of straightforward idea. I know that there may be any number of moves available at any given time. So I'll create a list to keep track of them all, and when I'm done, I'll return that list. How do I know what the possible moves are? Well, I need to do every hole in the board. I've got to go through every hole and see, is there a peg there? This is actually easy to do with my board representation, the way that I've set it up. A board has any number of tuples that represent the holes. For each of those holes, I say, is there a peg there? And that's done by asking, is there a truth value in board hole like that? As soon as I know that there's a peg there, I can now try all my different moves. This directions structure keeps track of 6 individual moves, where there's a delta column and a delta row. So I look at every delta row and delta column in those directions, each possibility. I need to find the midpoint, right? If I'm going to be jumping over, I have to make sure that the square in between actually has a peg. This checks to make sure that the from has a peg. I need to make sure that the one in the middle has a peg. And this can be captured by this sort of mathematical logic that says each of the deltas, delta C and delta R, is in fact an even number. So I look halfway between and I will find the right location. This is my midpoint, where once again I'm using a comma, a column, and a row to identify each individual hole on the board. If I'm starting from this location, some particular hole, and I try each of these directions, I can find the midpoint, and at the same time I can find the ending point. So I've got those computed, and now all I need to do is do a very quick check. If it is indeed the case that mid is a valid location, and there's a peg in mid. And the endpoint is valid. And it's not the case that there's a peg in the endpoint. All that together tells me I've got to move. And this, again, all comes back on a representation of the board, which I took several iterations to get right. And in fact, in this video, I've only shown it to you like it came out magically. It takes a while to get it just right, and you have to have a feel for it. To be able to represent the board, that's one thing, but to make it possible to quickly and efficiently compute all the possible moves that are available. So now I have my move is now ready. And my move is going to look like the following. It's going to be a tuple with 3 values. It's going to be the particular hole that has the peg, and the delta C and the delta R, which are being applied. That's what my move is. So I'm going to make a quick note of that. Move is a triple, which starts with a hole, delta C, and delta R. So this is my moves function. We can actually try it out, and we have to make sure that we're making progress. I have my initial board already set to go. We're going to skip the inner point at 4, 2. And again, I no longer worry about understanding what's in there. I'm going to look at these functions that I'm writing. What are the valid moves available on the board? There are 2 moves that are available. If I have that middle square of the triangle, if that middle one is empty, I can jump northeast or I can jump northwest. Those are 2 possible moves. The northeast jump starts from this location 2, 0, which is the second to left peg on the lower row. If I'm jumping northwest, it's 6, 0, the second to the most peg on the right. After a while, when you have a representation, you feel a lot like Cypher in the Matrix, where you say, I no longer think about the solitaire game, I just look at these numbers and I know exactly what they mean. Coming up with the right representation is critical for this whole algorithm. And you could spend hours wasting your time because you had a poor representation. As it is now, I have my board. I have the ability to generate any number of moves. And now, I'm ready to tackle the third and final step. How do I make a move? And correspondingly, how do I undo a move? Let's talk about making a move first. To making a move, I'm going to update the board state. Well, the board is nothing more than a dictionary that keeps track of for every hole whether there's a peg there or not. So my make move is actually kind of simple. I assume that my move is a triple that starts with a hole, delta C, and a delta R. So what do? I say, OK, from this move, I'm going to extract out the delta C, the delta R, and the move from that. And I want to say a very simple thing, basically replaying what I did before. Take the peg that used to be in the midpoint, which is this location here. I'm just going to copy it. Take that peg that used to be in that midpoint, and take the peg in the end. And for this move to work, very simple. You say board, the peg that used to be in the hole is now gone. Board, the peg that used to be in the middle, he's now gone. Board, the ending point, he now is a peg, which is all that I need to do. I'm just updating the state of the board as determined by the representation and the move that I had. Given this structure, you can imagine that the undo is no more complicated. And in fact, I'm just going to do the exact same thing, just this time, I'm going to undo. Everything else is the same. The only thing that's different is that when I undo a move, I'll do it in reverse order. I'm going to take the ending point and say, you know what? I got to remove that peg which had ended up in that location. The middle point, I got to put that peg back because I've just undone that move, so I can't eliminate it. And finally, the originating spot, yep, he gets his peg back. Now that we have a move, making a move and undoing a move, let's try it out. Always good to try out baby steps every time you add some new code to your code base. We now have the ability to create an initial board. And I'll skip the center spot. There's my board. I have the ability to identify what the moves are given that particular board. Let's look at the very first one. This is in this list, this is the first one that you see here. It's the move, which is a northwest jump. It starts from the peg, which is second to the right on the bottommost row, and it jumps up and over and fills up that middle spot again. So if I wanted to make that move on the board, this is what my board looks like. Now, if I look at that, it may be hard to find all the things that I'm looking for, but let's look for the things that I know. Initially, 4,2 was false. Initially, there was no peg in the center spot. After making this move, 4,2 is true. There's a peg there now. Initially, at 6,0, there used to be a peg. Right over, if I find it here, 6,0, there used to be a peg. But now, there is no peg. That's because I've jumped from there. And finally, I removed another peg from the board. Which one did I remove? I removed the one which is directly northwest of that location, which is the location 5,1. So I at least have some evidence that I've been able to produce the board the way I want. I can even check by saying, well, what are the moves that are available now? And now you see I've got 3 different moves that are available. Just to make sure all my functionality is working, let me undo that move because I want to make sure that that works before I continue. I'm going to undo the move that I just executed. And now my moves that are available are right back at the beginning, those 2 that I had. We now have everything in place to write the final function that will call the solve method. As you know, the solve method starts with a board and a path. Well, we need to kick that process off. So let's write a function. That function will be called solve specific. I give it a board, and I want to solve it. Solve a board and return the path of moves. So I start with an initial board, and given that, I need to call that solve method that we had before. Solve board and some path. Well, I've got to start with the path here, which is initially empty, an empty list. If I call solve, when I'm done, path should record an actual sequence of moves that will solve the peg solitaire game. So presumably once this is done, I will, for every move in path, print it out. Let's try it out. Starting again at my initial board, which is an initial where I leave out the center peg. And from this point, let me solve that board specifically. Specific. Off it goes, and it comes back with a sequence of moves. There was a little delay there, about a half second to a second. And if I actually carried out these moves, you would see that the final board state that's left, it's false, 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 false everywhere. The only one that's true is 4,0, the center peg on the bottommost row. So this is a really interesting final ending of this code. We were spending so much time on all the details, trying to get the representation right, spending our time on the moves. All that work is immediately put to practice in this solve function, which I wrote long ago. It really is the case for the brute force algorithm. All of the work is in the representation. If you can find the right way of representing the board state, and you can find the right way to represent what a move is, and make it possible to execute those moves, and presumably make it possible to undo the moves as well, then you have a framework in place to be able to solve any number of problems that would otherwise seem impossible because they're too tedious or you can't see an intelligent solution to finding out a way to solve that problem. At this point here, I will leave it to a project to write a small little program that will print out that board so you can actually see how nice it looks. And then you could, with your own eyes, you could verify that that's a good solution. But I've at least convinced myself that these are the sequence of moves that will activate I know that the solve method stops only when the length of the path is equal to the board length minus 2, which tells me I've made the requisite number of moves, and I can see that there's only one peg left standing. So as far as I'm concerned, I have a working solution here for solving peg solitaire, but it's so much more. You can take this exact same framework and solve so many other different kind of problems, and I can speak from experience. I've used this approach for 30 years. When you're trying to solve simple problems that defy any immediate solution, write a brute force. It might run overnight, it might run for 2 days, but you might come up with an answer. And that's something that's extremely valuable as another tool in your toolbox when it comes to working with algorithms.